Out here, light is no longer something that warms your skin. It's a traveler, ancient, fragile, and stretched thin across the black. 120 light-years away, in the quiet constellation of Leo, a faint shimmer of starlight carries a secret. The James Webb Space Telescope has seen something extraordinary, chemical signs that whisper of oceans, air, and life itself. A world named K218b may hold the ingredients for existence beyond Earth. Could this be the first place in the universe to look back at us? If you find wonder in the vast unknown, take a deep breath, like and subscribe, and join us on this cosmic voyage. Let's begin. It began with a flicker, barely perceptible in the flood of cosmic noise. A thread of infrared light reaching us after a journey of 120 years, carrying with it the chemical story of another world. When Webb's instruments decoded that light, what they found would shake the foundations of science itself. The signal arrived not as an image, but as data, a long, delicate heartbeat of photons captured in the silence of space. Each tiny pulse represented a single piece of light that had left a distant sun long before the first airplanes took flight on Earth. But to the James Webb Space Telescope, it was everything. A whisper from a world we had never seen, waiting to be translated. The telescope's sensors are so sensitive they can detect a candle burning on the moon. From its cold perch a million miles away, Webb gazed toward the constellation Leo, where a faint red star named K218 burns with the dim persistence of a dying ember. Around that star, hidden in its glare, circles a planet roughly 8 times the mass of Earth. It does not shine. It does not call attention to itself. Yet the light passing through its thin veil of atmosphere carried the unmistakable fingerprints of life. To reach us, those photons had traveled through unimaginable emptiness, past clouds of gas that once birthed stars, past comets wandering between systems, past the invisible filaments of dark matter that shape the universe itself. By the time that fragile signal reached Webb's golden mirrors, it had weakened to almost nothing, a handful of photons scattered across infinite dark. But they were enough. When the first spectrum appeared on the monitors back on Earth, the scientists were quiet. They had seen graphs like this thousands of times before, a pattern of dips and peaks revealing the molecules that make up an alien sky. But this one was different. Between the familiar traces of methane, water vapor, and carbon dioxide lay another signature, one no one expected to see. A subtle curve at a precise wavelength, repeating across multiple observations. The unmistakable chemical note of dimethyl sulfide. On Earth, that molecule exists for one reason only: life. It is the breath of oceans, the scent of plankton drifting beneath the waves. No volcano, no storm, no inorganic process can make it. To find it light years away was to find, indirectly, something breathing, something living. And so, what began as a faint, nearly invisible flicker became a revelation, a single thread of light unraveling the solitude of our species. For the first time in history, humanity had detected the presence of life, not in its own backyard, not in a nearby moon or neighboring planet, but across the interstellar gulf. As the data continued to stream in, the realization sank deeper. The cosmos was not silent. It had been speaking all along, softly, patiently, in the language of light. We had simply needed the right kind of eyes to finally hear it, orbiting a dim red dwarf in the constellation Leo. K218b sits in the narrow band of space astronomers called the Habitable zone, where liquid water can exist. It's a world 8 times Earth's mass, cloaked in hydrogen and mystery. From a distance, the system looks unremarkable, just another faint star among billions. But hidden in that faint red glow is a planet that challenges everything we thought we knew about what makes a world alive. K218b is what scientists call a Hycean planet, a term born from the blend of hydrogen and ocean. It is neither a gas giant like Neptune nor a rocky Earth twin. Instead, It exists in the in-between, with a deep global ocean beneath a dense hydrogen-rich sky. To picture it, imagine standing on the shore of an endless sea under a perpetual dusk. The sky above you glows with the faint red light of a star that never rises nor sets. Its light is soft and constant, more like the glow of embers than the blaze of a sun. The air, though alien, might shimmer faintly, thick with hydrogen, scattering light in hues of violet and crimson. In that atmosphere, molecules drift and mingle, forming the delicate chemistry that sustains oceans below. The numbers behind this planet are humbling. K218b is roughly 8.6 times more massive than Earth and about 2.6 times its size. Its gravity would press 3 times harder against your feet than our own worlds, and yet that very gravity holds its atmosphere in a steady embrace. The surface, if one exists at all, lies far beneath layers of cloud and vapor, an unseen ocean stretching down for hundreds of miles. Beneath that atmosphere, scientists believe, could be a sea unlike any other, not made purely of water, but of water infused with hydrogen and methane. In such an ocean, pressures would be immense, but stable, temperatures warm enough to nurture the chemistry of life, yet cool enough to preserve it. It is an alien balance, a planet built not for comfort, but for endurance. Its parent star, K218, is smaller and cooler than our Sun, but remarkably steady. Unlike many red dwarfs that flare and rage unpredictably, K218 burns with quiet persistence. Its energy reaches the planet in just the right amount, gentle, consistent, and ancient. Over billions of years, that steady light could allow ecosystems to emerge and evolve, sheltered beneath the planet's atmospheric veil. Astronomers have long searched for a second Earth, a twin to our fragile home. But K218b is no mirror. It's a revelation. It tells us that life may not need an Earth-like world to begin. It may bloom in places where the rules are different, where oceans are warm with hydrogen instead of salt, and the sky glows red instead of blue. When scientists first named it K218b, the label was purely technical, a catalogue entry in a database of distant worlds. But now, that simple name carries something more, a reminder that somewhere beyond the stars, another ocean may be breathing beneath an alien sun. On a quiet morning, a line appeared in the data, one molecule among millions. Dimethyl sulfide. On Earth, it's made only by living things. Its discovery on K218b turned an exoplanet into the most compelling candidate for alien life ever found. For months, scientists had been poring through an ocean of information collected by the James Webb Space Telescope. Streams of light converted into numbers, numbers into patterns, and patterns into meaning. Most days, the data was routine: hydrogen, methane, carbon dioxide, familiar gases seen in the atmospheres of countless worlds. But then came this line, subtle, persistent, too specific to be a glitch. It appeared in multiple readings, under different instruments, at different times. A signature that refused to disappear. At first, they thought it was noise, an artifact of the telescope's sensors, or contamination from Earth's own atmosphere. Independent teams, using separate datasets, confirmed the same spectral fingerprint. Dimethyl sulfide, DMS, a molecule that, on our planet, arises only from the activity of life. On Earth, the scent of DMS rides on the ocean breeze. It's created by microscopic phytoplankton, tiny, sunlit organisms drifting in the upper layers of the sea. When they bloom and die, they release this compound, which then rises into the atmosphere, helping form clouds that cool the planet. A small molecule with a planetary impact, and now, somehow, it had been found more than 100 light-years away. The realization rippled through the scientific community like an electric current. What if those same molecular processes were happening on K218b? What if, beneath that hydrogen-rich sky, alien oceans were alive, filled with microscopic organisms, breathing and transforming their planet just as ours do? If confirmed, It would mark the first detection of life beyond Earth, an answer to a question humanity has whispered to the stars for centuries. But the implications reached even further. It would mean that life is not rare, that biology is not an accident of Earth's geology or chemistry, but a fundamental feature of the cosmos itself. The announcement was cautious. Scientists are trained to doubt, to challenge, to test. A possible biosignature, the headlines read. But beneath the measured language lay awe. After all, this wasn't oxygen, which can appear from non-biological processes. It wasn't methane, which can leak from rocks. This was a molecule with no known inorganic source. The odds of it forming naturally on a lifeless world were vanishingly small. And so, that single spectral line became a mirror reflecting our place in the universe. One molecule, an invisible trace in a band of light, bridged the gulf between stars and stirred something deeply human: wonder. As scientists stared at the data, they realized they weren't just studying a planet. They were witnessing a moment in history. A quiet signal from across space and time saying, in its own chemical language, life is not alone. The James Webb Space Telescope drifts 1 million miles from home, its golden mirrors open like petals in the cold. From its silent perch, it captures the faintest heat of distant worlds like K218b, glowing softly against the void. It exists in a realm of silence, balanced at a gravitational point known as L2, where the pull of the Earth and the Sun cancel each other out. There, in that delicate stillness, Webb orbits unseen, always facing away from the Sun, its vast silver sunshield protecting it from warmth and light. On one side, darkness stretches infinitely. On the other, the dim glow of our solar system fades into nothing. Webb watches from this place of eternal twilight, its golden mirrors gazing into the heart of the cosmos. Each of its 18 hexagonal mirrors reflects not sunlight, but the ancient warmth of creation itself. The metal, coated in microscopic layers of gold, is tuned to detect infrared light, the faint thermal glow that all objects emit, even worlds too distant to see. But through Webb's sight, it is alive with heat, galaxies forming, stars igniting, planets breathing beneath alien suns. Building Webb was an act of faith as much as engineering. It is a machine designed to look backward in time, so sensitive it can detect the heat of a single candle on the moon. Its instruments operate colder than Pluto's surface, chilled to near absolute zero to avoid contaminating its own readings. Every observation it makes must be perfect, because there are no second chances. In the freezing vacuum, there is no technician to tighten a screw or replace a part. Webb must perform flawlessly, forever. From this distance, Earth is a pale blue memory. The telescope was sent here not to look back, but to look beyond, to peer through the cosmic dust that hides the beginnings of stars and the atmospheres of faraway worlds. Each photon that strikes its mirror is a messenger from a time long gone. Some of the light Webb sees tonight left its source before humans even existed. When Webb turned its golden eye toward the faint red glow of K2-18, the instruments came alive. Layer by layer, observation by observation, the telescope collected light that had traveled 120 years to reach its sensors. It separated that light into colors the human eye cannot see, revealing a pattern, a fingerprint, left by the molecules swirling in a distant planet's sky. The beauty of Webb lies not only in its power, but in its patience. It does not see with speed or brilliance, but with endurance, gathering the faintest whispers of the cosmos and holding them until they can speak. From its vantage point in the dark, it listens to the universe breathe. And when that breath carried the story of K218b, the heat of its oceans, the chemistry of its air, the shimmer of life, a telescope built by human hands, adrift in the cold, had become a bridge between worlds. Every molecule speaks in color. When a planet passes in front of its star, starlight filters through its atmosphere, leaving behind a spectral fingerprint. Webb's detectors read this light like ancient script, revealing water, methane, carbon dioxide, and something far more intriguing. To most of us, light is simple, bright, or dim, warm or cold. But to astronomers, it is a language, and every wavelength is a word. The universe speaks through these subtle variations, encoding its secrets in the way light bends, fades, and absorbs. When Webb turns toward a distant star, it doesn't just see the planet passing in front of it. It listens to the way the starlight changes as it travels through that alien atmosphere. Imagine sunlight passing through a stained glass window. Each color that shines through is filtered by the minerals in the glass. The same is true for a planet's atmosphere. Molecules absorb light at specific wavelengths, creating patterns, tiny notches carved into the spectrum. To the human eye, these gaps are invisible. To Webb, they are a translation key. Each missing color tells a story of what floats in that planet's sky. When K218b passed before its red dwarf star, Webb's instruments captured the most delicate of these changes. Every orbit, the telescope gathered more light, stacking observation upon observation until a hidden message began to emerge. Water vapor, methane, carbon dioxide, molecules that together suggest a balance, a dance of chemistry that could nurture oceans below. But then came something else, a faint dip at a wavelength that didn't belong to the usual suspects. The data whispered of a molecule that on Earth exists only because life puts it there. Its presence was so subtle that it could easily have been dismissed as noise. Yet it reappeared again and again, across multiple datasets, confirming that this was no error, it was a signal, a whisper through color. This process, turning light into meaning, is called spectroscopy. It is one of the most elegant tools in science, a way of reading the invisible. Long before we can ever visit these worlds, long before any probe can touch their oceans, we can already taste their air, molecule by molecule, from across the stars. Light carries everything we need to know. For scientists, each spectrum is like a page torn from a cosmic diary. They trace its curves and valleys, the signatures of gases that shape a world's climate, its weather, even its biology. And when the data of K218b arrived, that diary read like poetry, its verses written in wavelengths, its meaning both profound and familiar. In that moment, humanity realized that light is not just illumination, it's conversation. Across the blackness of space, one planet was speaking to another, using the oldest medium in existence. And for the first time, we had built something capable of answering back, dimethyl sulfide, a molecule born of oceans, plankton, and living breath. To find it elsewhere is to find life's signature. On K218b, the detection was clear, the probability, 99.7%. The universe had whispered, and we had finally learned to listen. On Earth, dimethyl sulfide drifts invisibly through our skies, carried on the salt-heavy winds that rise from the sea. It is the faint, organic scent you catch after a storm passes over the ocean, the perfume of plankton, of life itself. Microscopic phytoplankton release it as part of their natural rhythm, breathing in sunlight, exhaling chemistry. This single molecule connects the water to the air, the smallest organisms to the largest climate systems. It regulates clouds, helps seed rain, and cools our planet. It is, in many ways, the breath of the biosphere. And now, that same breath seemed to echo across 120 light-years. The James Webb Space Telescope had captured traces of it in the atmosphere of K218b, a distant, hydrogen-shrouded world orbiting a red dwarf star. The readings were delicate, almost impossible. The molecule's infrared fingerprint is faint, buried deep within a symphony of other gases. Yet Webb saw it clearly, again and again, its signature unwavering. For the scientists studying the data, disbelief was the first response. Every potential source of error was checked. Could it be contamination from Earth? A trick of the instrument? A chemical coincidence? One by one, the possibilities fell away. The remaining explanation was the most extraordinary. And the simplest: life. Dimethyl sulfide is unique among biosignatures. Oxygen can come from sunlight splitting water molecules. Methane can leak from volcanoes or chemical reactions within rocks. But DMS is stubbornly biological. On Earth, there is no known non-living process that makes it. It is born only from metabolism, from cells that breathe, reproduce, and die. To detect it on another planet is to glimpse an ecosystem at work, unseen but undeniable. If confirmed, this discovery would mark a turning point in human history, the first clear sign that life exists beyond Earth. Not imagined, not theoretical, but detected in the very chemistry of an alien atmosphere. The first proof that biology is not confined to one blue world orbiting a yellow star. And what a thought that is! That perhaps, somewhere beneath the soft red light of a distant sun, oceans roll beneath hydrogen clouds, filled with microscopic life forms drifting in warm, perpetual twilight. That their collective breath, billions of tiny exhalations, travels across space as a message, a quiet announcement of existence. The universe, it seems, doesn't shout its secrets, it whispers them. Through the faintest lines of a spectrum, through the colors of invisible light, it tells us that we are not alone. Dimethyl sulfide is more than a molecule, it's a voice. The breath of an alien ocean carried across the stars, finally reaching our ears after more than a century of travel. And as scientists stared at the data, they realized something profound. The cosmos was exhaling, softly, steadily, and for the first time, humanity was listening closely enough to hear it, 120 degrees Fahrenheit. Not too hot, not too cold. A planetary sweet spot, warm enough for oceans to flow, cool enough for molecules to thrive. In the scale of cosmic possibility, K218b rests at the perfect balance for life. Temperature is the quiet architect of existence. Every living thing we know, from the simplest microbe to the human mind, depends on it. It governs how water moves, how chemistry unfolds, how energy flows through a world. Too cold, and atoms freeze into silence. Too hot, and molecules fall apart before they can dance. Life happens only in that narrow middle ground, where warmth invites movement. For Earth, that range is a rare gift. We orbit at just the right distance from our sun for liquid water to exist, and our atmosphere keeps it there, steady and gentle. But K218b has achieved this balance in a completely different way. Its star, a small red dwarf, emits only a fraction of our sun's heat, but the planet's thick hydrogen atmosphere acts like a perfect blanket, trapping warmth and distributing it evenly across the globe. The result? A steady 120 degrees Fahrenheit, a number so improbable, so ideal, that it seems almost deliberate. In earthly terms, that's the heat of a hot summer day, the warmth of desert sand at sunset, the gentle burn of a human fever. It is warm enough to stir oceans and drive chemistry, yet cool enough for liquid water to persist for eons. On K218b, this temperature may never waver. While our planet swings between winter and summer, day and night, this alien world rests in eternal equilibrium, its warmth wrapped around it like a second skin. For scientists, this discovery was breathtaking. The stability of such a temperature suggests that the planet's atmosphere is more than protective. It's self-regulating. As energy from its star enters the upper layers, the hydrogen clouds absorb and redistribute it, creating a planetary thermostat that maintains perfect conditions for life. Even the night side, forever turned away from its sun, remains warm enough to keep oceans from freezing. Imagine that for a moment. An entire world without seasons, without the icy extremes of polar nights or the scorching deserts of equatorial heat. A planet of constant twilight and steady warmth, where oceans never freeze and winds move in graceful, endless circulation. In that unbroken balance, life could flourish without fear of drought or frost. Energy would flow in harmony, fueling biological processes without interruption for billions of years. Here on Earth, life fights against change. On K218b, life would exist within constancy. Each organism, each cycle, could evolve not through survival of the harshest, but through the refinement of stability. The very concept of stress, of scarcity, might not even exist there. 120 degrees Fahrenheit. A number that reads like coincidence but feels like poetry. The same warmth that shapes our own lives, our hearths, our blood, our breath, may be the universal temperature of life itself. Across the vastness of space, the same physics, the same chemistry, the same gentle heat seem to conspire toward one simple outcome: a world that can breathe. And somewhere beneath that hydrogen sky, in oceans as warm as thought, something may be doing exactly that. Scientists believe K218b's surface may be covered in vast hydrogen-rich oceans, deeper than any on Earth. Imagine waves rolling beneath a rose-colored sky, lit by a red sun that never truly sets. It's a vision that stirs something ancient in the human spirit, the endless ocean, the cradle of life, stretched out beneath an alien star. The oceans of K218b may be hundreds of miles deep, layered with chemistry utterly unlike our own. The upper layers could shimmer with liquid water mixed with hydrogen, while the depths below might compress into exotic ices that exist only under immense pressure. Down there, light would fade to silence, and the boundary between sea and sky would blur into mystery. Astronomers call worlds like this Hycean planets, a term born from the fusion of hydrogen and ocean. They occupy a new category between rocky super-Earths and gaseous mini-Neptunes, wrapped in a thick, life-friendly atmosphere and blanketed by water. K218b was the first of these worlds to show chemical signs that such an ocean might not just exist, it might be alive. To stand beneath that alien sky would be to experience perpetual twilight. The star it orbits, a cool red dwarf, emits a soft crimson glow, dim to human eyes, but constant, steady, and warm. There would be no true sunrise or sunset, only subtle shifts of hue as light filters through the planet's hydrogen-rich clouds. The sea below might gleam in shades of copper and violet, reflecting the distant starlight like molten glass. On Earth, our oceans are restless. They breathe through tides, churned by the gravity of the moon and the heat of the sun. But K218b's seas might move to a slower rhythm, guided by the planet's tidal lock with its star. One hemisphere basks eternally in light, the other in darkness. Yet the powerful winds and deep currents circulating between them could keep the entire planet's waters warm and stable. Those winds, thicker and heavier than ours, might ripple across the ocean's surface, carrying the scent of chemistry, the breath of life. If life exists there, it may thrive beneath the surface, far from the radiation of the red dwarf above. In those murky depths, alien plankton could bloom, feeding on the faint light that filters through. Their biochemistry might be entirely different, based not on oxygen, but on hydrogen or methane. Yet the rhythm would be familiar. The slow pulse of ecosystems building, consuming, and transforming their world. Some scientists imagine colossal storms sweeping across this world, where lightning flashes illuminate the horizon like veins of energy through a living organism. Others envision calm, mirror-like waters stretching into infinity, each wave a soft echo of the planet's slow heartbeat. And perhaps, in the deeper layers, where pressure turns water into exotic forms of ice and heat seeps upward from the core, life thrives as it does around Earth's hydrothermal vents, feeding not on sunlight, but on energy born from the planet itself. K218b's oceans remind us that water is not just an earthly treasure, it is a cosmic one. Wherever it flows, the possibility of life follows. And in those endless, alien seas beneath a red sky, the universe may have found yet another way to dream itself alive. Unlike Earth's thin air of nitrogen and oxygen, K218b's atmosphere is dominated by hydrogen. It acts as a planetary blanket, trapping warmth and creating a global equilibrium, an entire world held in gentle thermal embrace. Hydrogen, the simplest and most abundant element in the universe, is also one of the most mysterious when it gathers in great quantities. On Earth, it slips through our fingers, escaping into space, too light to be held by our gravity. But K218b is heavier, stronger. Its pull is 3 times that of Earth's, powerful enough to keep even hydrogen close. Over eons, that gas has swelled into a vast envelope around the planet, transforming its skies into a soft, insulating cocoon. In that hydrogen-rich world, the air would feel thicker, heavier, and far more compressive than our own. Light from the red dwarf sun would scatter differently there, painting the atmosphere in hues of crimson, gold, and deep violet. The sunlight that filters through it would be gentle, almost dreamlike, diffused across the endless ocean below, turning every wave into liquid fire. This thick atmosphere serves a crucial role. It keeps K218b's temperature steady, distributing the warmth from its star evenly across the planet. While the day side faces eternal light and the night side rests in perpetual darkness, the hydrogen acts as a conveyor of heat, ensuring that neither burns nor freezes. This balance is what allows its oceans to remain liquid, a perfect equilibrium where chemistry can thrive. Hydrogen's properties make this balance possible. It traps infrared radiation efficiently, amplifying the planet's greenhouse effect, but in a way that doesn't overheat. Instead, it maintains a steady warmth, an invisible current of energy that circles the world in silence. The hydrogen moves like a slow tide through the upper layers of the atmosphere, carrying whispers of methane and water vapor along with it, creating a delicate dance of gases that defines the planet's climate. To scientists, this kind of atmosphere is more than an environmental condition. It's a living laboratory. Beneath those layers, pressures rise, temperatures stabilize, and molecular interactions accelerate. Hydrogen's abundance provides a fertile ground for organic chemistry, where carbon, nitrogen, and oxygen can mingle freely. These are the building blocks of life as we know it, and hydrogen is the stage upon which they perform. Imagine standing beneath such a sky. The air would glow softly in perpetual twilight, the clouds above thick and smooth like the surface of milk. You'd feel the weight of the world's gravity pressing down, the warmth surrounding you like a humid embrace. Lightning could ripple within those high clouds, illuminating the horizon in flashes of pink and gold. Below, the ocean would respond in kind, waves rolling in slow motion, as if time itself had learned to move gently here. If life exists beneath that hydrogen canopy, it may look nothing like the forms we know. Its cells might rely on hydrogen chemistry instead of oxygen, its metabolism tuned to this unique atmosphere. But it would breathe, it would change, and it would endure, just as life does everywhere it finds a foothold. K218b's hydrogen atmosphere may be its greatest gift. In that endless, invisible blanket, warmth and chemistry weave together, creating not chaos, but calm. The planet is not a storm-tossed giant nor a frozen wasteland. It is serenity incarnate, a world suspended between light and dark, wrapped forever in the universe's gentlest element. K218b is tidally locked, its day side forever facing its star while the night side lies in eternal twilight. Yet the thick atmosphere redistributes warmth so efficiently that both hemispheres could remain friendly to life. To understand what that means, imagine standing on a shore where the sun never moves. It hangs motionless in the sky, neither rising nor setting, suspended in eternal afternoon. On one side of the planet, light pours endlessly across oceans tinted crimson by the glow of the red dwarf above. On the other side, night has no dawn, only the soft shimmer of starlight diffused through hydrogen clouds. Between them lies a vast ring of twilight, a region of perpetual dusk that circles the entire globe. Here, time loses meaning. There is no day to mark beginnings, no night to signal rest. Instead, the planet lives in a kind of slow, unbroken rhythm. Winds sweep from the bright side toward the dark, carrying warmth in great, looping currents. The thick atmosphere acts like a planetary engine, cycling heat, air, and moisture across hemispheres until the temperature evens out. The result is a world that, despite its extreme geometry, might feel surprisingly calm. On Earth, tidal locking sounds like a death sentence for habitability. One side burns, the other freezes. But K218b defies this expectation. Its hydrogen-rich atmosphere, dense, deep, and dynamic, prevents catastrophe. The day side absorbs energy from the star, but the gases quickly distribute it through convection and high-speed winds. By the time that warmth reaches the far side, it's enough to keep the oceans liquid even under the dim glow of alien constellations. In this balance, life could find many homes. The day side might host floating microbial mats that bask in the steady light, converting the red star's glow into chemical energy. Meanwhile, the twilight ring, the borderland between endless day and endless night, could harbour temperate regions where conditions mirror Earth's most comfortable climates. Even the night side, bathed only in scattered light, could sustain deep-sea ecosystems beneath the planet's global ocean. Imagine drifting across those seas in the eternal dusk of the twilight zone. The horizon would stretch infinitely, glowing faintly where day and night meet. The clouds above would shift slowly, reflecting gradients of colour from fiery rose at the edge of the day side to violet and indigo as the darkness deepens. The stars would never fade. They would hang motionless, their reflections trembling softly across the alien waves. And yet, despite the stillness, the world would hum with energy. Currents flow, clouds swirl, thunder rolls faintly in the far distance, echoing across the endless water. K218b breathes, not in the rapid rhythm of Earth, but in slow, planetary inhalations. A steady exchange of light and shadow, heat and calm. To call it the planet that never sleeps is not to say it's restless, but that it is always alive. Its oceans never freeze. Its atmosphere never settles. Even in perpetual day and endless night, there is movement, a balance so perfect it feels almost deliberate. Somewhere in that unending twilight, beneath skies that never darken or brighten, life may be dreaming. Not in cycles of waking and sleeping as we know them, but in an eternal state of gentle, illuminated stillness, a world perpetually awake beneath the watchful eye of its crimson sun. Gravity there is 3 times stronger than Earth's. A human weighing 150 pounds here would weigh 450 there. But this same gravity keeps its oceans and atmosphere secure, holding life close and safe. Gravity is the quiet sculptor of worlds. It shapes planets, binds stars, and keeps galaxies from dissolving into chaos. On K218b, it does more than pull, it protects. Every droplet of water, every wisp of hydrogen in the sky is held fast by its immense embrace. It is the invisible hand that gives the planet its form and its serenity. For us, that gravity would be crushing. Standing on a solid surface there, if such a surface exists, your knees would tremble beneath a weight you were never meant to bear. Each heartbeat would feel slower, heavier, as if time itself had thickened. Even lifting a hand would be an act of quiet defiance. But for K218b's oceans and its atmosphere, that same force is a blessing. It binds the world together, keeping its gases from drifting into space and its seas from evaporating into the void. Because of this immense pull, the planet has been able to hold on to its thick hydrogen envelope for billions of years, a feat Earth could never accomplish. Our own gravity is too weak, allowing light gases to escape into space long ago. But K218b's gravity holds even the lightest elements tight, weaving them into a permanent shroud that stabilizes the planet's climate. Without that force, there would be no atmospheric blanket, no warm oceans, no possibility of life. Imagine the beauty of that equilibrium. The atmosphere pressing gently downward, the ocean pushing upward in response. 2 vast layers of matter locked in an eternal embrace. The weight of the sky there would be immense, yet perfectly balanced. It is not oppressive, but nurturing. That weight traps heat, redistributes energy, and keeps the planet's chemistry active. The same gravity that would crush our bones may also cradle something delicate, life itself. In such an environment, life would need to adapt. On Earth, whales have evolved massive muscles to glide effortlessly through water. On K218b, similar adaptations might exist in creatures we can only imagine. They would be strong and fluid, shaped not by light or air, but by the gentle resistance of gravity itself. Every movement would be deliberate, every structure built to endure. Their forms might be squat, compact, dense, designed for a world that never lets go. Even light behaves differently under such pressure. The hydrogen atmosphere would scatter it more slowly, bending it softly as it descends toward the ocean. Colors would deepen, and sound would travel farther. Waves might roll more slowly, heavy but graceful, as if time moved through thicker air. It would be a world that feels solid, grounded, eternal. Gravity often feels like a burden to us, a force we struggle against. But on K218b, it is the architect of possibility. It holds oceans in place, it holds warmth in the air, it holds the planet's soul together. Without that immense pull, K218b would be just another frozen rock orbiting a distant star. Instead, it is something far more beautiful, a world whose weight gives it life. Perhaps that is the quiet lesson hidden among the stars, that what holds us down is often what keeps us alive. Its parent star, K2-18, is smaller and cooler than our Sun, but far more stable. It burns with a quiet persistence that could last trillions of years. Time itself bends slower around such stars, an eternity for evolution to unfold. K2-18 is what astronomers call an M-dwarf, or red dwarf, tiny compared to our Sun, but immensely long-lived. While our Sun blazes with the ferocity of youth, burning through its fuel in roughly 10 billion years, a red dwarf sips its hydrogen slowly, cautiously, like a candle meant to burn forever. Its glow is faint but steady, its rhythm unbroken. In a universe of violence and chaos, red dwarfs are the monks. Quiet, patient, and enduring. To the naked eye, K2-18 would appear as a dim ember against the velvet sky, invisible without the aid of telescopes. Yet up close, it would fill the heavens of its planet with a crimson hue, washing the atmosphere in warm tones of copper and rose. The light would feel softer than sunlight, less blinding, more enveloping. Plants or photosynthetic organisms, if they exist on K2-18b, might have evolved to absorb this red-shifted energy, using pigments unlike anything on Earth. They would turn the ocean not green, but perhaps shades of purple, black, or even silver, designed to drink in every available photon. What makes K2-18 so remarkable is its stability. Many red dwarfs are known for violent flares, sudden eruptions of radiation that can strip nearby planets bare. But K2-18 seems calm, its light steady over time. This quietness offers something rare in the cosmos: consistency. For life to arise, a world must be left alone long enough for chemistry to become biology, and biology to become consciousness. K2-18's gentle glow provides that sanctuary. The faint light of a red dwarf changes how time feels. On Earth, days and seasons give us a rhythm. The rising and setting of the sun divide our lives into measurable moments, but on K2-18b, bathed in the eternal dusk of its star, time would stretch. There would be no sharp transitions between day and night, only the soft pulse of a steady glow. For the beings that might evolve there, existence would unfold slowly. This longevity has cosmic implications. Red dwarfs like K2-18 will outlive every other type of star. When the last sun-like stars have burned out and the galaxy has gone dim, the red dwarfs will remain. still glowing faintly in the dark. Life that forms around them could persist for trillions of years, long after Earth and even the Milky Way have faded into memory. In that sense, K218b orbits not just a star, but a promise of endurance, a cosmic hearth that will never go cold. While our species looks to the stars for short flashes of wonder, the inhabitants of such worlds, if they exist, would know something we can only imagine. K2O-18's glow is not the brilliance of youth, but the wisdom of time. A quiet light that doesn't demand attention, yet never fails to shine. It is the kind of light life could build an eternity upon. A star that burns softly enough for evolution to dream without interruption, beneath a sky that never truly darkens. High above K218b's oceans, carbon atoms compress into crystal storms. Diamonds fall like snow through methane clouds, scattering starlight across a shimmering alien sea. It sounds like a dream, or perhaps a fantasy drawn from the imagination of poets, but it is science. In the crushing pressures of K218b's atmosphere, the ordinary becomes extraordinary. Methane, abundant in its hydrogen-rich skies, is made of carbon and hydrogen. Under immense heat and pressure, the bonds that hold those atoms together begin to break. The carbon atoms fall downward like invisible dust, and as they descend through the dense atmosphere, they are pressed tighter and tighter until they crystallize. The result? Diamond rain. Millions of tiny gems forming and falling endlessly into the ocean depths below. This is not unique to K218b. Astronomers believe similar phenomena occur on Neptune and Uranus, where lightning storms split methane and forge diamonds in the deep. But on K218b, the conditions are magnified, hotter, heavier, and far more dynamic. Here, entire layers of the atmosphere could be filled with crystalline clouds. Imagine standing beneath such a sky, flashes of silent lightning illuminating clouds that sparkle faintly, each droplet a fragment of light turned solid. The air would shimmer as the diamonds fell, catching the red glow of the distant star and scattering it in every direction like cosmic glitter. To any life forms below, this rain would not be rare, it would be part of the planet's cycle, just as rain and snow are part of ours. The diamonds might sink into the deep, dissolve into strange ices, or collect on the ocean floor, compressed under pressures that would shatter any earthly machine. Over time, these layers of crystal could become geological features, shining strata that mark the slow heartbeat of the world. And above it all, methane would paint the sky. On Earth, methane is invisible, but under K218b's crimson sun, it could tint the atmosphere in surreal shades of violet and rose. The horizon might glow faintly blue, fading into red as the star's light filters through the haze. Sunlight, soft, dim, and steady, would bend through these clouds, creating a perpetual, muted twilight. Every reflection on the ocean's surface would ripple with hidden color, every raindrop a prism. Methane is also more than decoration, it's a clue. Its presence, alongside water vapor and carbon dioxide, points to active chemistry at work. These molecules can interact to form the complex carbon structures that serve as precursors to life. In that way, K218b's storms are not just meteorological, they are creative. The same processes that forge diamonds might also forge molecules that breathe, grow, and change. When we imagine alien beauty, we often picture exotic landscapes or strange creatures. But K218b's wonder is in its balance of physics and art. Diamond rain is not a myth, it's the poetry of chemistry written across a planet's sky. Somewhere out there, beneath those glimmering clouds, light from a distant red star catches on a falling crystal. It glints, briefly, then vanishes into the deep. That glint, tiny, silent, eternal, is the reflection of a truth too vast to ignore. The universe is not cold or empty. It is alive with beauty. Even in its storms, scientists noticed what wasn't there. Ammonia, common in lifeless gas giants, was absent. Something was actively removing it, altering the atmosphere. That something could be life itself. In science, Discovery often comes not from what we find, but from what we fail to. When the James Webb Space Telescope peered into the atmosphere of K218b, it didn't just see the presence of methane, water vapor, and dimethyl sulfide. It saw the distinct absence of something expected: ammonia. On most planets like this, hydrogen-rich and massive, ammonia is abundant. It forms naturally as nitrogen and hydrogen combine under high pressure and heat. Yet here, in the layers of gas swirling above the planet's ocean, the signature of ammonia was faint, almost completely gone. To the scientific mind, that absence was deafening. It suggested that something was disrupting the normal chemistry, a process that consumes or transforms ammonia faster than it can form. There are explanations, of course. Maybe a hidden chemical cycle unique to K218b's atmosphere is at work. Perhaps ultraviolet radiation from the red dwarf star breaks down ammonia molecules before they can accumulate. But another possibility, one far more exciting, whispers through the data that life is responsible. On Earth, biology constantly reshapes our atmosphere. Plants draw in carbon dioxide and release oxygen. Microbes beneath the oceans fix nitrogen and consume ammonia, altering its global balance. These same patterns could be playing out on K218b, only on a planetary scale. If microbial life thrives in its oceans, it could be using ammonia as part of its metabolism, breaking it down, cycling it through biochemical processes, just as our own biosphere does. The numbers make the mystery even deeper. The ratio of methane to carbon dioxide on K218b doesn't match a purely chemical origin. In a lifeless atmosphere, certain reactions should reach equilibrium, producing predictable levels of ammonia as a byproduct. But Webb's data revealed something out of balance. A system that seems actively maintained. That imbalance is precisely what scientists look for when hunting for life. On Earth, it's called a biosignature disequilibrium, the chemical fingerprints of a world that's breathing. Imagine the unseen mechanisms that could drive such change. Beneath the hydrogen sky, in warm alien seas, colonies of microorganisms might thrive, each microscopic cell a living engine converting nitrogen compounds into something else entirely. These processes could subtly alter the composition of the atmosphere above, a planetary metabolism mirrored in light years of distance. The planet itself becomes a living system, its sky shaped by the collective work of countless unseen organisms. In a sense, the missing ammonia is like a negative photograph of life, a shadow where something should be. It's the chemical silence left behind when living things are too small, too distant to see directly. Yet even that silence carries meaning. Perhaps the greatest beauty of K218b's discovery lies not in the molecules that shine brightly, but in the quiet gaps between them. In those gaps, we find the fingerprints of life's subtler artistry, the way it consumes, transforms, and balances. The absence of ammonia may not sound dramatic, but in that emptiness, the cosmos has left a hint. Something on that world may be at work, rearranging its air with purpose. And as humanity listens to those spectral whispers, we are reminded of an old truth, that sometimes the most profound evidence of life is not in the noise it makes, but in the silence it leaves behind. The planet's atmosphere holds a balance of methane, carbon dioxide, and water vapor, a chemical melody echoing Earth's biosphere. It's as if the planet is breathing in time with the cosmos. Every living world, whether Earth or something far more distant, composes its own atmospheric song. Each molecule is a note, each reaction a rhythm. Together, they create harmony, or discord. When scientists examined the spectral data from K218b, they found a pattern too balanced, too intentional, to be random: methane and carbon dioxide in just the right proportions, water vapor drifting in quiet abundance, and ammonia, the one discordant note that should have been there, missing entirely. It wasn't just chemistry, it was choreography. On Earth, this same trio, methane, carbon dioxide, and water, is what gives our air its vitality. Methane is created by life, by bacteria and organic decay. Carbon dioxide fuels plants and regulates temperature. Water vapor keeps everything connected, the medium through which energy flows. These gases exist in constant motion, never static, always adjusting to the needs of the biosphere. When scientists looked at K218b, they saw a familiar equilibrium, a living balance where none should exist. The laws of physics dictate that in a purely inorganic world, these molecules shouldn't coexist in stable amounts. Methane reacts easily with oxygen and carbon dioxide. One consumes the other until one disappears. Yet on K218b, both persist. Something must be replenishing them, maintaining the balance. It's the same dance we see in Earth's own sky, a self-regulating system sustained by life's invisible hand. Imagine that atmosphere as an orchestra. Methane plays the warm, organic tones, the baseline of life. Carbon dioxide provides the structure, the framework that keeps temperature and chemistry in tune. Water vapor is the melody, light and ever-shifting, carrying energy and rhythm across the globe. If one rises too high, the others respond, pulling the system back into harmony. The result is a planetary equilibrium, an atmospheric composition that sounds less like chaos and more like intention. For scientists, this was the moment the data stopped being numbers and started being something deeper, a sign of connection. Light years away, another world might be following the same chemical score that our own planet plays. The same gases, the same ratios, the same silent breath of a living world. If life exists on K218b, it may be microscopic, adrift in its warm oceans or clinging to droplets in its dense hydrogen air. Yet its presence would echo outward, rewriting the chemistry of an entire planet. Every molecule of methane, every whisper of water vapor would carry the fingerprint of countless unseen organisms. Life would not just live on K218b, it would become K218b, inseparable from its climate and chemistry. In the vastness of space, this balance feels like a kind of music, an invisible rhythm that connects one living world to another. The same universal tune, played in a different key. Perhaps that's the real beauty of discovery. Not just that we've found a planet that might harbor life, but that its air hums with a pattern we already recognize. A melody we've been hearing all along, reflected back to us from across the stars. Somewhere, beneath a red dwarf sun, K218b inhales and exhales. Its oceans shimmer, its clouds drift, and its atmosphere sings, a perfect chemical symphony of life's quiet persistence, a 99.7% probability. In science, that number borders on the miraculous. The odds that the dimethyl sulfide signal is random noise? 3 in 1,000. Almost impossible. Almost. Certainty is rare in science. It's not declared lightly, nor earned easily. Each data point must survive endless scrutiny. Every equation rechecked, every variable challenged. But when astronomers ran the numbers on K218b's atmosphere, one result refused to disappear. Dimethyl sulfide. The molecule that, on Earth, only life creates. The more they refined the data, the clearer the signal became. The 99.7% figure didn't come from intuition or optimism. It came from mathematics, from models that simulate how light behaves as it passes through alien air, from algorithms that strip away noise, and from the cold, impartial logic of probability. When the final analysis was complete, the answer was undeniable. There was only a 0.3% chance that what Webb detected was an illusion. In the realm of discovery, that's the thin edge between speculation and revelation. But what does 99.7% really mean? In simple terms, it means the data aligns almost perfectly with what scientists would expect if dimethyl sulfide truly exists in K218b's atmosphere. Each molecule leaves a precise spectral fingerprint, a pattern of dips in the light spectrum that no other compound can mimic. Webb saw that fingerprint again and again, across multiple observations, at multiple wavelengths. To dismiss it would require an alternative explanation more improbable than life itself. In physics, there's a term called the 3 sigma result. It's the statistical threshold where a finding becomes strong evidence. To pass it is to step beyond coincidence. K218b's DMS reading exceeded that mark. It wasn't absolute proof, science rarely offers absolutes, but it was close enough to shift the weight of history. For the researchers involved, this number, 99.7%, wasn't just a statistic. It was a heartbeat, a quiet pulse of excitement beneath the calm professionalism of their reports. They knew what it meant. It meant that for the first time, we may have measured not just the conditions for life, but life's direct signature itself. And yet, humility tempers discovery, because the universe is vast and filled with complexities beyond human imagination. Could there be a chemical process, unknown to us, that creates dimethyl sulfide without life? Perhaps. But if so, it would have to operate under conditions we've never witnessed. It would mean rewriting the chemistry we know, a task as monumental as confirming alien biology. Science advances through this tension, belief balanced by doubt, wonder balanced by rigor. Every discovery must be strong enough to inspire, yet sturdy enough to withstand skepticism. That's the power of numbers. They anchor awe in reason. So when astronomers say 99.7%, what they really mean is this: we are standing at the edge of something extraordinary. It's not a leap of faith, but a step built on evidence, precision. In that final decimal point lies the story of centuries of human curiosity, of equations written in candlelight, of telescopes pointed at the unknown, of minds daring to ask if we are alone. 3 chances in 1,000 that we are mistaken, 997 that we are not. And somewhere in that narrow space between uncertainty and discovery, humanity takes its next breath, listening, waiting, ready to believe. Artificial intelligence combed through millions of light curves, searching for patterns too subtle for human eyes. In that sea of data, it found a whisper, a signal that said, "We are not alone." The James Webb Space Telescope sends back an ocean of information, streams of light transformed into data, billions of numbers that together form a portrait of the cosmos. It is more than any team of humans could ever manually study. Within that digital tide lie the hidden fingerprints of stars, planets, molecules, and perhaps life. But like all vast things, the truth is buried in the noise. That is where artificial intelligence has become humanity's new sense, an eye that never blinks, a mind that never tires. AI algorithms trained in spectral analysis have learned to read light as if it were language. They can detect infinitesimal patterns in brightness, trace subtle distortions in color, and find consistencies so faint that even the most experienced astronomer would overlook them. These algorithms don't feel wonder. They don't dream or hope. They simply see, purely, precisely, relentlessly. When the data from K218b arrived, it was these silent mathematicians that first noticed the anomaly. Amid the predictable fingerprints of hydrogen, methane, and carbon dioxide, there was a spectral line that did not fit the standard models. A slight deviation, barely measurable, yet repeated in multiple datasets. It didn't shout its presence. It whispered it, buried in the soft noise of cosmic light. The AI flagged it. A signal, it noted, consistent with dimethyl sulfide, the molecule of life. At first, the human teams dismissed it. After all, the idea that an algorithm might casually find evidence of extraterrestrial biology seemed absurd. But as they verified the data, checking, recalibrating, cross-referencing, they found that the AI was right. The signal was real. In a poetic twist, the discovery that could change humanity's understanding of existence didn't come from a moment of human intuition, but from a machine that understood the universe only through numbers. Yet in that moment, human and machine worked together seamlessly. Curiosity guided the questions. Computation found the answers. What makes AI powerful is not that it replaces human thought, but that it extends it. Where we see chaos, it sees pattern. Where we see impossibility, it finds probability. The algorithms designed for Webb can compare thousands of planetary atmospheres in seconds, building models of how light behaves as it interacts with gases, clouds, and even oceans. It can detect what human eyes were never meant to see, chemical whispers from worlds we may never touch. There's something profoundly human in that collaboration. We built these tools out of logic and curiosity, yet they return to us something deeply emotional. The possibility that we are not alone. The AI doesn't understand the magnitude of its finding. It doesn't know what it means to glimpse life beyond Earth. But we do. And perhaps that is the future of discovery, a harmony between intuition and computation, between wonder and precision. The algorithm found a whisper. We gave it meaning. Somewhere in the endless expanse, a signal flickered through space, and a machine noticed. But the moment it reached human hands, that data transformed into a question older than civilization itself, a question we now dare to answer. We built machines to help us see deeper into the dark. And one night, quietly, they showed us something alive looking back. Unlike Earth's water, K218b's oceans are infused with hydrogen, creating liquid conditions that could remain stable from freezing to boiling temperatures. Life there might swim in chemistry we can barely imagine. When we think of oceans, we think of something familiar, blue, cool, and brimming with the ingredients of life as we know it. But on K218b, the very concept of ocean takes on a new meaning. These are hydrogen oceans, not pure water, but a complex mixture of hydrogen, water vapor, methane, and possibly ammonia, layered beneath a dense atmospheric shroud. It's a liquid realm sustained by physics we only partially understand, one that challenges our definitions of habitability itself. On Earth, hydrogen is elusive. It escapes easily, vanishing into space, leaving behind heavier gases like nitrogen and oxygen. But on a world 8 times Earth's mass, gravity holds it fast, binding it into both sky and sea. There, under high pressures and steady warmth, hydrogen mixes intimately with water. This union changes everything. The ocean's boiling point rises, its freezing point falls, and the boundary between liquid and gas begins to blur. The result is a sea that remains stable across an enormous range of temperatures, perhaps from just above freezing to hundreds of degrees Fahrenheit. It's a strange thought that beneath K218b's soft red sky, waves could roll endlessly at 200 degrees without evaporating. In those depths, light from the red dwarf above might never reach, replaced instead by the planet's inner heat, glowing softly from below. Hydrothermal vents could dot the ocean floor, spewing minerals and warmth into the darkness. Chemistry, restless and creative, would thrive there, forging complex molecules in the crucible of heat and pressure. If life exists in these hydrogen seas, it would be unlike anything we know. It might metabolize hydrogen or methane instead, using chemical gradients rather than sunlight as its source of energy. Such organisms could be microscopic, forming dense colonies in the upper layers of the ocean where the chemistry is most dynamic. Or they might drift in slow motion, suspended in the thick, buoyant liquid. Their biology tuned perfectly to an environment where gas and water are one and the same. Scientists call such worlds Hycean planets, a word that fuses hydrogen and ocean. It's a new class of exoplanet that may vastly outnumber Earth-like ones. For every rocky, temperate world, there may be dozens of these oceanic spheres wrapped in hydrogen blankets, quietly orbiting dim red stars. If life can survive here, it could exist everywhere. The more we study hydrogen oceans, the more we realize how little we truly know about the limits of biology. On Earth, we once thought life required sunlight, oxygen, and mild conditions. But then we found bacteria thriving in boiling acid, in the vacuum of space, and beneath miles of ice. If life can survive there, why not here, in a sea that is more chemistry than water? Imagine standing at the edge of that ocean, if one could stand at all. The waves would move slowly, their crests heavy and shimmering under a rose-colored sky. Each ripple would refract light differently, scattering crimson and violet across the surface. And below, the depths would glow faintly with trapped heat. An ocean that doesn't just sustain life, but creates it, molecule by molecule, in a never-ending experiment written by the universe itself. On K218b, the ocean isn't merely a feature, it's a possibility incarnate. A reminder that even in the most alien conditions, nature finds a way to turn chaos into rhythm and silence into song. If life exists beneath those hydrogen waves, it may not breathe oxygen. It might breathe hydrogen itself, an alien metabolism perfectly adapted to its home. On Earth, oxygen is the rhythm of our existence. We inhale it, burn it for energy, and exhale the carbon dioxide that feeds the rest of the biosphere. But in the grand theatre of the universe, oxygen is not the only song life can sing. Life, in its most fundamental form, is not loyal to any single molecule. It only needs a way to move energy from one place to another, and hydrogen, abundant and eager to react, could be the key to an entirely different kind of biology. In K218b's deep oceans, where hydrogen saturates every current, the chemistry would favor reactions unlike any on Earth. There, an alien organism might not breathe in the way we do at all. Instead of oxygen molecules entering tiny lungs or gills, hydrogen could flow directly through cell-like membranes, fueling chemical reactions that extract energy from the planet's rich mixture of gases. Metabolism, in this world, would not be a process of burning, but of balancing. Imagine a microscopic organism floating just below the surface, bathed in red starlight filtering through hydrogen mist. Its biology might resemble the earliest forms of life on Earth, primitive, efficient, and patient. Instead of splitting water to create oxygen as our plants do, it might split hydrogen molecules, releasing subtle traces of methane or other byproducts back into the air. Over time, countless generations of these creatures could fill the ocean, subtly reshaping the planet's atmosphere, maintaining the strange equilibrium that scientists now detect from across the stars. It's a humbling thought that life might breathe in reverse, exhaling what we consider uninhabitable gases and thriving in conditions that would destroy us instantly. Yet, that is the beauty of evolution. It molds itself to whatever canvas the universe provides. Where we see poison, life sees opportunity. Astrobiologists have long suspected that hydrogen-based life could be widespread. On the icy moons of our own solar system, like Europa or Enceladus, microbes might survive by combining hydrogen and carbon dioxide deep below frozen crusts. On K218b, those same principles could unfold on a planetary scale, with an entire biosphere driven not by oxygen, but by hydrogen chemistry. The implications are enormous. If life can exist here, it means biology is far more versatile than we ever imagined. It doesn't require Earth's delicate balance of gases, nor its sunlight, nor its familiar chemistry. It only requires energy, molecules, and time. Three things the universe provides in abundance. Picture the stillness of those oceans. The water is thick, the air heavy, the red dwarf sun a constant ember in the sky. In that steady warmth, alien cells drift and divide, exchanging molecules with their surroundings, feeding an invisible cycle of creation and decay. The entire planet may be breathing through its sea, every wave a lung, every molecule a heartbeat. Perhaps that's the greatest revelation of all. Life doesn't just adapt to its world, it becomes it. If something lives beneath the hydrogen seas of K218b, its breath is the ocean itself, its pulse, the slow movement of gas and heat across the planet. And somewhere, beneath that rosy twilight sky, in a sea too heavy for our lungs, something utterly unlike us may be inhaling, exhaling, and living, proving that life, at its core, is not defined by what it breathes, but by the miracle that it breathes at all. Some models suggest a biosphere vast enough to alter global chemistry. This isn't a lonely pond of microbes. It could be an entire living ocean, changing a planet's sky. When scientists speak of potential life on K218b, they don't just mean isolated microbes drifting aimlessly in the dark. The evidence hints at something larger, more interconnected. A biological network powerful enough to shape its entire atmosphere. On Earth, our biosphere does this every moment of every day. From the algae in our oceans to the forests on land, life continuously modifies the air we breathe, balancing gases, absorbing heat, and transforming energy. If K218b's atmosphere mirrors this same kind of dynamic balance, it suggests that its seas are not silent, they are alive. Picture that alien ocean not as an empty abyss, but as a world within a world. Its surface glows softly under the red light of its star, while beneath, layers of water and hydrogen mingle like mist and fire. Here, microbial colonies could thrive in staggering abundance, feeding on chemical gradients rather than sunlight. Instead of photosynthesis, they might rely on chemosynthesis, harvesting energy from the planet's natural chemistry, converting methane, hydrogen, and carbon dioxide into organic matter. If such a biosphere exists, it would be vast. With oceans potentially hundreds of miles deep, even a sparse microbial density could amount to unimaginable biomass. Billions upon billions of living cells swirling through the depths, each one contributing to the planet's global metabolism. Together, they could release gases that rise into the atmosphere, forming the very spectral signatures that Webb has detected. Water vapor, methane, carbon dioxide, and dimethyl sulfide. This invisible exchange between ocean and sky is the same dialogue that sustains our own planet. On Earth, phytoplankton in the sea produce most of the oxygen we breathe. They are the unseen architects of our climate, regulating temperature and chemistry from beneath the waves. On K218b, the same principle could apply, only there, the ingredients are different, the reactions stranger, and the outcome even more profound. Imagine what it means for an entire world's atmosphere to be a reflection of life below. Every molecule of dimethyl sulfide might represent countless organisms exhaling together. Every absence of ammonia might mark the chemical footprint of their consumption. The planet itself becomes a living system, its biology and climate inseparable. Such a biosphere would likely be ancient. Red dwarf stars burn for trillions of years, offering more than enough time for evolution to experiment endlessly. Over eons, life on K218b could have refined its chemistry into perfect equilibrium, maintaining an atmosphere not by accident, but by adaptation. What Webb detects today may not be the spark of new life, but the calm breath of something that has existed for billions of years. If true, K218b isn't just another exoplanet, it's an ecosystem on a planetary scale. Its clouds, its weather, even its temperature might all be shaped by living processes. From space, that influence appears as delicate shifts in light. Up close, it might feel like the heartbeat of a world. And as we look at the faint glimmer of that distant planet, one thought lingers. If life can transform an entire sky, then perhaps the stars themselves are filled with unseen worlds, quietly alive, their atmospheres breathing softly in the dark. How does Webb see a world hidden in the glare of its star? Through coronagraphs, delicate masks that block starlight so faint, planetary whispers can emerge. Like shielding your eyes to see fireflies beyond a floodlight. It is one of the most extraordinary acts of precision in human history, to see something billions of times fainter than the light beside it. A planet like K218b does not shine with its own fire. It reflects only the faintest shimmer of its star's light. Against that brilliance, it is practically invisible, a ghost orbiting an inferno. Yet somehow, the James Webb Space Telescope can find it, isolate it, and even read the colors of its unseen air. The secret lies in an instrument born from both art and physics. The coronagraph. Originally developed to study the sun, it works by masking the light of the star itself, creating a small, artificial eclipse within the telescope. Once the overwhelming starlight is removed, what remains are the faint whispers of everything around it: planets, dust, and molecules. Imagine standing in a dark field, trying to see fireflies while a spotlight blazes nearby. You'd shield your eyes, narrow your gaze, and wait for your vision to adjust. That's what Webb does. Except it's doing it from 1,000,000 miles away, blocking light that's traveled for more than a century. Its mirrors must align to within nanometers, fractions of the width of a human hair, so that the masking is perfect. A single imperfection, a vibration, or a beam of stray light could drown out the planet's signal completely. When the coronagraph engages, the star vanishes into engineered darkness, and in that darkness, K218b appears, not as an image, but as a pattern in the remaining light. Webb doesn't see the planet the way we see with our eyes. Instead, it measures how the star's brightness dips when the planet passes in front of it, and how the light's color shifts as it filters through the atmosphere. From those subtle changes, scientists can reconstruct an entire alien sky. This process is both delicate and profound, a marriage of engineering and imagination. Every measurement is a conversation with the invisible. Webb listens to photons that have traveled for over 100 years, analyzes how they've been shaped by hydrogen, water, and methane, and translates them into data humans can understand. The precision required is staggering. The telescope must remain colder than any winter on Earth, its instruments shielded from even the faint warmth of the Sun, Earth, and Moon. Its mirrors, made of gold-plated beryllium, are so finely tuned that they could detect the heat of a single candle on the Moon from here on Earth. And yet, through all that sensitivity, it finds balance. It blocks the overwhelming light of stars, not to destroy it, but to reveal the fragile beauty hidden in its shadow. When Webb peers at K218b, it performs an act of cosmic artistry, sculpting darkness into meaning. It takes the impossible, seeing a world across 100 light-years, and turns it into data, color, and story. Through its mechanical grace, Webb reminds us that discovery is often not about seeing more, but about learning to block out the noise. In the hush left behind, entire worlds emerge. And so, by dimming the brightest light in the sky, humanity has learned to glimpse something even brighter, our own reflection, shining faintly from another star. To detect K218b is like spotting a candle beside a lighthouse from 1,000 miles away, yet Webb does it with precision measured in billionths of a meter. It's almost absurd to imagine. A planet so dim, so faint, that it reflects barely a whisper of light compared to the fiery blaze of the star it orbits. If you stood near K218b's sun, you could fit over 1,000,000 Earths into its glare. Yet across a gulf of 120 light-years, the James Webb Space Telescope can tell when that faint planet passes in front of its star and even decode the invisible ingredients of its atmosphere. It is a feat that defies intuition, a triumph not of strength, but of sensitivity. The comparison is poetic because it's true. The red dwarf K218 shines tens of billions of times brighter than the light reflected by its planet. Imagine trying to see a firefly flutter near a lighthouse beam on the far edge of an ocean, and not only noticing it, but measuring the shape of its wings by the way its glow flickers. That's what Webb does every time it studies an exoplanet. The key lies in patience and precision. Webb doesn't take snapshots, it listens. Over hours and days, it records the faintest fluctuations in starlight as the planet crosses its face. Each time, the light dims ever so slightly. To the naked eye, the difference would be imperceptible. But to Webb's instruments, it's as clear as a heartbeat in the dark. The telescope can measure changes as small as 1/10,000th% in brightness. From that, it can infer the planet's size, its orbit, its density, and even the molecular composition of its skies. All of this happens because of the extraordinary engineering that underlies Webb's vision. Its gold-coated mirrors, aligned with nanometer precision, focus light onto detectors that can sense infrared radiation finer than a whisper. The smallest vibration, the faintest temperature fluctuation could ruin a reading. So the telescope drifts in near-perfect stillness, protected by a sunshield the size of a tennis court. It's not brute force that lets us see these worlds. It's balance, calm, and extraordinary patience. To the scientists studying the data, the miracle isn't just that Webb can detect K218b, it's that it can understand it. By studying how the starlight changes color as it passes through the planet's atmosphere, Webb translates those variations into chemistry. Methane, carbon dioxide, water vapor, perhaps even dimethyl sulfide. Every shift in light is a clue, every fraction of a wavelength a sentence in an ancient language of photons. And what makes it most extraordinary is how small the difference truly is. The signal Webb reads from K218b is a mere handful of photons, light particles that have crossed interstellar space for over a century. By the time they reach the telescope's mirrors, they are ghosts of themselves. Yet from those ghosts, humanity builds meaning, models, and awe. This is the art of detection at its purest. It's not about conquering distance, but about embracing sensitivity. It's about learning to find the faint, steady pulse of truth hidden beneath overwhelming brightness. And maybe there's something poetic in that, because it's what humanity has always done. From the first astronomers who traced constellations across the night sky, to the engineers who sent a golden telescope into the dark, we've always been trying to find the firefly beside the searchlight, to find, in the vastness of light and noise, that one soft signal that tells us there's something out there. Unlike chaotic worlds torn by storms, K218b may be remarkably calm. Its atmosphere smooths out extremes, creating a single global climate, an eternal summer for life to flourish. In the tapestry of planets we've observed, calmness is rare. Most worlds are violent places: Jupiter's endless tempests, Neptune's supersonic winds, Venus's crushing greenhouse haze. Even Earth, beautiful and alive, is a world of extremes: deserts and glaciers, tempests and droughts, balance born from contrast. But K218b may be different. There, under a hydrogen-rich sky and the steady light of a red dwarf, peace could reign. Its dense atmosphere, far thicker than our own, acts as a vast equalizer. It absorbs energy from the eternal day side and gently carries it to the endless night, wrapping the planet in uniform warmth. Winds flow slowly, not in violent gusts, but in graceful, planetary currents. No hurricanes rage, no polar storms howl, just a slow, unending circulation, a breathing world where every region shares the same soft twilight glow. Computer models suggest that this kind of balance is more than theoretical. It's almost inevitable for a world like K218b. The hydrogen that fills its skies is exceptionally efficient at transferring heat. Where Earth's thin air lets temperature swing between scorching deserts and freezing poles, K218b's atmosphere blurs the boundaries. The same thermal energy that might spawn chaos elsewhere here becomes harmony. Imagine it, an oceanic world bathed in permanent dusk. The surface temperature never drops low enough for ice to form, nor high enough for water to boil away. Clouds drift lazily across rose-colored skies, reflecting the muted light of the red dwarf above. The waves below move to a slow rhythm, driven not by seasons or weather, but by the steady heartbeat of the planet's inner heat. This equilibrium could make K218b one of the most stable environments for life in the galaxy. But on K218b, life would have time, billions of years of unbroken calm, to evolve with patience instead of urgency. There would be no natural disasters to erase progress, no harsh seasons to cull fragile beginnings. Evolution could proceed like a symphony played in slow motion, every note perfect, every rhythm eternal. Even its star plays a role in this serenity. Red dwarfs, though dim, are consistent. K218 burns softly, steadily, for trillions of years. Its energy output is gentle, its lifespan effectively infinite. This quiet persistence offers its planet something our own world will one day lose: time. While Earth will face a dying sun in a few billion years, K218b's home star will still be glowing, still warming its oceans, still providing the light that sustains it. Perhaps, beneath that tranquil sky, life has already taken advantage of this endless summer. Maybe it thrives in floating colonies, drifting across hydrogen seas, never fearing extinction, never knowing chaos. A biosphere not forged in struggle, but in equilibrium, a rare and beautiful possibility in a universe that so often favors turbulence. K218b may be proof that not all worlds are born into conflict, some are born into peace. A planet balanced perfectly between light and dark, warmth and cold, life and silence. A world where time flows like water and existence never rushes. An eternal summer, lit softly by a red sun, waiting for us to listen to its quiet harmony. With each world Webb studies, the definition of habitable expands. Life, it seems, doesn't just adapt, it redefines the possible. There was a time when humanity believed life could only exist on worlds like ours, planets with blue skies, green continents, and oceans of liquid water, orbiting a sun much like our own. But each new discovery chips away at that narrow vision. The James Webb Space Telescope, with its golden mirrors turned toward the dark, is teaching us something profound, that the universe itself learns. It evolves. It revises its own rules, showing us that life is not a fragile exception, but a resilient expression of the cosmos. Every time Webb observes a planet like K218b, it rewrites what habitable means. Once, we imagined life confined to oxygen and sunlight. Then we found microbes thriving in the sulfurous vents of Earth's oceans, in radioactive waste, in the frozen lakes of Antarctica, in clouds high above Venus. Now we're beginning to see that life might flourish beneath hydrogen skies, in oceans without air, under the glow of red stars that never truly rise or set. Each discovery stretches the borders of imagination, and with it, the borders of possibility. What if life doesn't need Earth's gentle climate, its oxygen-rich air, or its narrow window of comfort? What if the universe creates life in forms we can't yet recognize, in chemistries that breathe hydrogen, or feed on methane, or communicate through electrical pulses in liquid metal seas? If nature has taught us anything, it's that it abhors limitation. It adapts endlessly. In that sense, K218b is not just a world, it's a teacher. It invites us to let go of anthropocentrism, the idea that Earth's formula for life is the only recipe that works. The balance of gases in its atmosphere, the warmth beneath its hydrogen blanket, the potential of its dimethyl sulfide signal, all of it whispers the same truth. Webb's mission, then, is not only scientific, but philosophical. It's forcing us to confront the possibility that life is not rare at all, that it may be a natural outcome of chemistry wherever conditions allow energy to flow and molecules to mingle. If that's true, then the universe is not an empty expanse, dotted with isolated miracles. It is an ecosystem, vast and evolving, learning through trial and error how to make complexity out of chaos. Each observation Webb sends home is a lesson. Some worlds teach us what life needs, others teach us what it doesn't. Together, they outline a spectrum of possibilities so wide that habitability begins to look less like a specific set of conditions and more like a universal inclination, a tendency for matter to organize, to breathe, to become. Perhaps this is the greatest revelation of all, that life is not just something that happens in the universe, it is something the universe does. With every discovery, the cosmos seems to whisper back our own story. You are not apart from me. You are what I have learned to create. And so, with each new world, Webb doesn't just show us how vast the universe is, it shows us how alive it might already be. The distance between K218b and its star allows it to absorb almost exactly the same energy Earth receives from the Sun, a cosmic coincidence that seems almost deliberate. It's a balance so delicate it borders on art. In astronomy, this equilibrium is known as the habitable zone, the orbital sweet spot where a planet's temperature is just right for liquid water to exist. Too close, and oceans boil into vapor. Too far, and they freeze into silence. Between those two extremes lies the golden mean of possibility, the thin line where warmth and chemistry meet. K218b rests precisely on that line. Though its star, K2-18, is far cooler and dimmer than our Sun, the geometry of its orbit compensates perfectly. It circles closer, so close in fact that a single year there lasts only about 33 Earth days. Yet because the star shines so softly, the total energy that reaches the planet's upper atmosphere is nearly identical to what our world receives. Two vastly different systems, one red and faint, the other yellow and bright, producing the same thermal balance. It's as if the cosmos has found multiple ways to write the same equation for life. From the perspective of physics, it's just math. Energy flux, distance, luminosity, all calculated to several decimal places. But from the perspective of wonder, it feels almost intentional, as though the universe is experimenting with variations of the same theme. What if I tried again, but with a different kind of sun? Because of this perfect positioning, K218b's hydrogen atmosphere doesn't overheat, nor does its ocean freeze. It exists in a zone where energy flows gently, evenly, where molecules can combine, separate, and recombine without destruction. This subtle balance allows complex chemistry to persist long enough to become something more. If K218b were even slightly closer to its star, its upper atmosphere might have boiled away billions of years ago. A bit farther, and its oceans could be locked in endless ice. But it sits in the exact place where warmth is eternal. Not scorching, not fleeting, steady. To a scientist, this precision is extraordinary. To a poet, it's divine geometry. This alignment also has a visual beauty. From the surface, if one could somehow stand upon it, the red dwarf would hang enormous in the sky, a glowing ember rather than a blazing disk. The light would bathe the world in soft rose and violet tones, never harsh, never blinding. And because the star's output is constant, that light would never wane. No seasons, no icy winters or burning summers, only continuity. Such constancy has profound implications for life. Evolution thrives on stability. With unchanging light and a uniform climate, the biosphere could progress undisturbed for eons. Patterns would emerge slowly, elegantly, in perfect harmony with the planet's rhythm. The distance between a planet and its star may seem a simple thing, just space and numbers. Yet it's everything. It's the line between chaos and chemistry, between darkness and dawn. K218b sits exactly where it must, absorbing just enough light to keep its oceans alive. And in that coincidence lies one of the universe's quietest miracles. That geometry itself, simple, impartial geometry, can cradle the conditions for life. Perhaps that is the truest form of symmetry, not in shapes or equations, but in existence itself, a harmony of distance, light, and time, arranged just right to make a world that breathes. While our sun will fade in 5 billion years, K2-18's red dwarf will shine for trillions. On that world, life could have eons to evolve beyond imagination. Time on K2-18b flows differently, not faster or slower, but deeper. Around a red dwarf star, the cosmic clock ticks at a gentler pace. These small, cool stars burn their fuel with exquisite efficiency, wasting nothing, living quietly while their brighter cousins live fast and die young. Our sun, magnificent as it is mortal. One day its light will swell, redden, and consume the worlds that now bask in its warmth. But the star K2-18 will still be burning softly, long after the Milky Way's familiar constellations have faded into history. Trillions of years. That's how long this quiet red ember will glow, steady and patient, bathing its planets in unending warmth. It's a timescale so vast that our entire civilization, the rise and fall of humanity, the building of cities, the birth and death of languages would be but a blink. Life on K218b, if it exists, could have evolved uninterrupted across epochs so long they defy imagination. Think of how far life on Earth has come in just 4 billion years, from single cells to thought, from ocean foam to art and consciousness. Now imagine giving life not billions, but trillions of years. What could it become? What shapes could intelligence take when given near eternity to dream? Perhaps the oceanic life on K218b began humbly, molecules dancing in hydrogen seas, forming membranes, exchanging energy. But with time so generous, evolution could explore every possible path. Intelligence, in whatever form it arose, would not need to rush. There would be no great extinctions to reset the clock, no dying sun to hurry its progress. Just endless time and endless potential. Red dwarfs are the universe's patient storytellers. They live quietly, casting soft light for longer than galaxies survive. While larger stars burn bright and brief, these small stars keep their worlds alive through eons of stillness. If life were to look for permanence, this is where it would find it. It's possible, then, that civilizations might emerge around such stars long after our own sun has faded. They could rise and fall in the distant future, unaware that once, long ago, another species looked their way and wondered. Or perhaps they already exist, ancient, contemplative beings whose evolution began before Earth was even formed, still thriving under that gentle red glow. To live on K218b would be to live within the ocean of time itself. Every moment there would carry the weight of eternity. The red sun would never die, the sky would never change, and the rhythm of existence would be measured not in days or years, but in eons. Maybe that is why the thought of this world feels so profound. It's not just about life, it's about time enough for life to reach its fullest expression. To create, to learn, to reflect, and perhaps even to understand the universe that made it. Our world races toward its inevitable sunset, but somewhere out there, under a dim red star that will burn long after ours is gone, another ocean waits, still, timeless, and alive. In that endless summer, time itself becomes the great teacher, and life, patient and persistent, listens, growing wiser with every trillion-year breath. From its chemistry to its climate, K218b feels eerily familiar. It's as if nature has written the same story again, only in a different language. When astronomers first examined the light from K218b, they expected difference. An alien world, strange and unrecognizable. Instead, they found echoes. Water vapor in its skies, methane and carbon dioxide in its atmosphere. A balance of gases that, though foreign in composition, resonated with something deeply known. Even its temperature, warm, temperate, forgiving, mirrors the cradle that nurtures life here on Earth. It's as though the cosmos, in its infinite creativity, decided to revisit a theme it once perfected, a planetary remix. The same melody played on new instruments, the same pattern of possibility, woven from different atoms, but carrying the same refrain. Life can happen here too. Look closely, and the similarities deepen. On Earth, our oceans regulate the planet's temperature, breathing clouds into the sky and drawing rain back down. On K218b, vast hydrogen-rich seas may do the same, trapping heat and creating gentle atmospheric currents that spread warmth across the globe. The cycle is slower, softer, perhaps endless. And just as Earth's life fills the air with subtle traces of chemistry, K218b's suspected biosphere may be altering its own skies, writing its existence into its atmosphere for distant telescopes to read. Even the light feels familiar in spirit. The red dwarf sun that warms K218b glows cooler and dimmer than ours, but steady. Its light never burns too bright, never fades too soon. Its warmth is constant, patient, a slower kind of sunrise that never quite ends. On that world, the concept of a day might not even exist. Instead, a perpetual dusk, painted in rose and violet, stretches across the horizon. To an Earthborn traveller, if such a journey were possible, it would all feel both alien and intimate. The air would shimmer differently. The gravity would press harder. The ocean, if you could touch it, would feel heavier and slicker than ours. Yet something about the rhythm of the place, the balance of warmth, the whisper of waves, the stability of light, would feel like coming home to a world we've never seen. And maybe that's no coincidence. Maybe the laws of physics, the constants of chemistry, and the instincts of nature all conspire to repeat what works. Wherever energy flows steadily and molecules have time to meet, life emerges. Different in form, identical in spirit. The shapes may change, the principle remains. It reminds us that Earth is not an exception, it's a pattern. A successful experiment the universe seems eager to repeat. Perhaps countless versions of this story are unfolding even now. Oceans breathing, skies changing, biology awakening under unfamiliar suns, each with its own colors, its own songs, its own reflections of a shared cosmic blueprint. K218b, then, is more than a discovery. It's a mirror, a reminder that life's story may not be unique, but universal, a tale told in countless dialects of chemistry and light. And if the universe truly echoes itself, then perhaps we are not just hearing the story of another world. Perhaps we are hearing the rhyme of creation, the same verse, sung again, across the endless sea of stars. The Photons Webb studies began their journey before human flight existed. When they left K218b, we were still dreaming of reaching the sky. That light, the faint shimmer that now tells us of oceans and life and distant suns, has been traveling through space for over 120 years. Every photon that strikes Webb's golden mirrors tonight began its voyage when the world below was lit by gas lamps, when horses still pulled carriages through city streets, when humanity had not yet flown. The Wright brothers had not taken their first leap into the air. The atom was still a theory. The stars were still eternal fires, not suns with planets of their own. And yet, while we were just beginning to imagine what it might mean to touch the sky, a handful of photons slipped free from a distant red star. They crossed the silent vacuum, passing countless other suns, weaving through the gravity wells of unseen planets, untouched, uninterrupted, unstoppable. For more than a century, they moved through the darkness, light that no eye would ever see until it reached the mirrors of a machine not yet conceived, built by a civilization not yet born. When those photons finally arrived, they carried with them a story, an imprint of a world orbiting that faint red sun. They held the secrets of K218b's atmosphere, the spectral fingerprints of its chemistry, the faint whispers of methane, carbon dioxide, and dimethyl sulfide. In their patterns, they contained evidence that life might exist, far beyond the reach of our own oceans. It's humbling to think that the data Webb now records is not a live broadcast, it's a time capsule. We are not seeing K218b as it is today, but as it was 120 years ago. A world frozen in a single moment of its ancient dance around its star. Perhaps its skies have changed since then, perhaps its oceans have deepened, or its atmosphere evolved. But we will never know those details, not until the light of those changes has time to reach us, more than a century from now. Every telescope, in this sense, is also a time machine. To look into the universe is to look backward, through layers of history written in photons. The farther we gaze, the older the light becomes. When Webb peers at distant galaxies, it sees them as they were billions of years ago. In the dawn of time, when it looks at K218b, it sees a century into the past, back when humanity was still tethered to Earth. That means the moment Webb confirmed the possibility of life on K218b, it was witnessing a world that existed before we knew flight, before we split the atom, before we looked up and truly wondered what lay beyond the stars. And there's something beautifully circular in that. The light left just as we began dreaming of reaching the heavens, and now, As it arrives, we have built the tools to finally listen to it. In those photons, separated by time and space, we see not just a planet, but a reflection of ourselves. A reminder that every discovery we make is also a reunion with the past. The universe sends us its memories, and we, curious, fragile, awake, learn to read them. So when Webb opens its golden eye to K218b, it's not just capturing data, it's catching a message that's been traveling toward us since before we could even imagine catching it. Light that began its journey when we first dreamed of flight, now whispering across time. You made it. You finally looked up. Looking at K218b is like peering into history. The life we see there now existed when our own world was just awakening to technology. Every time we gaze into the universe, we are looking backward. The light Webb collects is ancient. Each photon, a relic from a time long gone. When the telescope studies K218b, it's not observing the planet as it exists in this moment, but as it once was 120 years ago. A century-old snapshot of another world, preserved in the language of light. That means that if life exists on K218b, the biosignatures Webb is reading today, the methane, the water vapor, the dimethyl sulfide, belong to a version of that planet that no longer exists. Perhaps its oceans have deepened, perhaps its atmosphere has shifted, perhaps, just perhaps, that faint whisper of chemistry has grown into something more complex. We are seeing its past, not its present. And in a way, that's what makes the discovery so profound. Because while Webb stares into K218b's distant history, that same light carries us back to our own. The photons it studies began their journey through space when human flight was only a dream, when the first radios had just begun to hum, when the night sky above Earth was unpolluted and the stars still felt infinite. It's as though two moments, separated by a century and 100 light years, now touch across the void. The planet we are seeing and the civilization we once were, both caught in the same fragile moment of cosmic time. Perhaps the most haunting thought is this. The life we may be detecting on K218b could still exist right now, or it might have already vanished. But its signal, preserved in light, endures. Even if the oceans have boiled away, or if evolution has carried its creatures into new forms, their past still reaches us. Time, in this sense, is not a wall but a mirror, reflecting echoes of existence across the universe. And when we look into that mirror, we see ourselves. We see our own fragile balance of atmosphere and ocean, our own struggle to maintain habitability. The red dwarf's soft glow becomes our sun's distant cousin. The chemistry of another world becomes a reflection of our own. Astronomy, at its heart, is an act of memory. Every telescope is a collector of ghosts, ancient light, ancient life, ancient time. But the deeper we look, the more we realize that these reflections are not distant, they are intimate. They remind us that every world, every life, every civilization exists in the same cosmic current, flowing forward while its light drifts backward. So when we study K218b, we are not just learning about another planet, we are remembering our own. We are seeing a world as it once was, and in its reflection, we find our own story, how we began, how we dream, and how, one day, our own light will journey outward to be discovered by someone else looking back through time. Somewhere, in a future we will never see, another mind may one day catch the faint echo of Earth's light, our atmosphere, our oceans, our signals, and wonder what kind of life once lived here. And perhaps they too will whisper, as we do now. We are looking at a mirror through time. Among terabytes of raw numbers, scientists found the molecular equivalent of a fingerprint, a single, perfect clue that changes everything. When the James Webb Space Telescope observes, it doesn't send back images of shimmering planets or blue oceans. It sends back data. Vast oceans of it, numbers upon numbers, each one representing the brightness of light, the depth of a shadow, the subtle dip of a wavelength. To most eyes, it's meaningless noise, a blur of statistics without form or feeling. But hidden within that noise, the universe speaks softly. It whispers in patterns, and only those who know how to listen can hear it. For months, astronomers pored over K2-18b's spectral data. Hundreds of gigabytes turned into terabytes, each dataset a puzzle of photons collected from across the stars. The challenge was immense. To separate signal from static, truth from artifact. Most readings revealed the expected: water vapor, methane, carbon dioxide, molecules we already knew might exist there. But then, tucked deep in the spectrum, was something unexpected. A faint line, a subtle dip in the curve, a signal so small it could easily have been overlooked. Yet it was precise, consistent, repeating, undeniable. Dimethyl sulfide, the same molecule produced on Earth only by living things, mostly in our oceans. In one elegant, quiet curve, the data told a story no photograph ever could. Finding it was like uncovering a diamond hidden in sand, a single spectral feature among millions, but one that gleamed with impossible significance. It wasn't loud, it wasn't obvious, it was true. The scientists who found it didn't shout or celebrate immediately. They checked and rechecked. Was it noise? A glitch? A miscalibration? Webb's instruments are so sensitive that even a trace of cosmic dust or an imperceptible mirror shift could create false readings. But the signal remained, unchanged through every test, every correction. It was there, quiet, constant, real. To find such clarity in the chaos of cosmic data is a miracle of patience and precision. Each pixel of information represents photons that have traveled for over a century, through interstellar gas, through darkness unimaginable, just to end their journey in the heart of Webb's detectors. Those photons were absorbed, transformed into digital values, and translated into meaning. From that, a molecule emerged. A molecule that might mean life. Dimethyl sulfide became the diamond in the data not because it shouted louder than everything else, but because it fit perfectly. Its spectral fingerprint matched no chemical process known to occur without biology. It was as if, among the randomness of numbers, the universe had left us a signature, subtle, deliberate, and infinitely patient. What's striking is how quiet such a discovery truly is. There was no sudden flash, no dramatic signal, no voice from the stars, just a curve on a graph, smooth and precise, pointing to a molecule that shouldn't exist there unless something alive put it there. And that's the beauty of it. In the end, the most profound discoveries don't come from spectacle, but from stillness. The universe reveals itself not through noise, but through order. Amid terabytes of data and decades of searching, scientists found a single trace that could change everything. A fingerprint of life left on the wind of another world. A diamond, hidden in the dark, waiting 100 light-years for someone to find it. Within just 200 light-years, Webb has identified dozens of similar worlds. If even one more shows life's signal, the galaxy may be far more alive than we ever believed. The space around our sun, this small, quiet corner of the Milky Way, is not empty. It's a neighborhood of stars, thousands of them, each surrounded by its own retinue of planets. Many of these stars are smaller and cooler than ours, red dwarfs, ancient and steady, and around them orbit worlds not so different from K2-18b, Hycean planets, oceanic giants wrapped in hydrogen skies, basking in just the right amount of warmth. For the first time in history, we can see them clearly. The James Webb Space Telescope has turned its gaze toward this nearby cluster of suns, and what it's finding is extraordinary. In the narrow stretch of just a few hundred light-years, a distance that, in cosmic terms, is like the space between neighboring towns, Webb has already detected dozens of exoplanets that sit in the habitable zone of their stars. Some are rocky and Earth-sized. Others, like K2-18b, are larger, wrapped in thick atmospheres that glimmer faintly in the infrared. Each one holds a secret waiting to be read in light. And the data keeps growing. Every observation Webb makes adds another piece to a grand mosaic, a map of potential life. What's astonishing is the frequency. Worlds like K218b are not rare, they are common. They seem to appear everywhere Webb looks. For every 10 stars near us, at least one appears to host a planet capable of holding liquid water. That means, statistically, the galaxy could be teeming with habitable worlds, tens of billions of them. If even one more of those planets shows a hint of life, one more detection of dimethyl sulfide, or methane in chemical imbalance, or oxygen where it shouldn't exist, it would change everything. Because then, K218b would no longer be an outlier, it would be part of a pattern. Proof that life is not an accident, but a tendency, a natural outcome of chemistry and time. The thought is staggering. Within a region so small that our fastest spacecraft would still take millennia to cross it, there may be dozens, perhaps hundreds, of living worlds, each orbiting its own quiet sun, each following its own story. Some may be newly formed, where biology is still learning how to build itself. Others could be ancient, their oceans already long-lived, their ecosystems evolved far beyond our comprehension. And perhaps the most poetic part, all of this hidden web of life and light, exists right next door. We are not looking across the galaxy or into another cluster of stars. We're looking at our local space, the cosmic suburbs, the stretch of the Milky Way we might one day reach. It's humbling to realize that the search for life is no longer about if, but where. K218b opened the door, but Webb's ongoing discoveries show us there are many doors, each world a different possibility, a different story written in air and ocean. Maybe one day we'll listen to the light from another world and hear that same molecular whisper, the same spectral diamond that first changed everything. And when that happens, we'll know that the universe isn't just vast, it's inhabited, that we are part of a neighborhood filled with worlds breathing quietly in the dark, all orbiting their stars, all waiting for someone to notice. If life could take root on one world, it could take root on many. And maybe, just beyond the veil of distance, countless other skies are alive, each one, like ours, staring back into the infinite and wondering if they too are alone. Carbon, hydrogen, oxygen, nitrogen, sulfur. The same 5 elements form life on Earth, and perhaps on K218b. Different planet, same ingredients, same miracle. It's almost poetic how the universe repeats itself. Across trillions of miles and billions of years, nature seems to favor the same small handful of atoms, the same cosmic alphabet with which it writes the story of life. On Earth, those 5 elements are our foundation. They build our cells, our DNA, our oceans, our air. They compose the food we eat, the air we breathe, the thoughts that pass through our minds. And now, the same elements appear to shape the chemistry of a world more than 100 light-years away. Carbon, the backbone of complexity. Hydrogen, the simplest and most abundant. Oxygen, the bridge between energy and life. Nitrogen, the architect of proteins. Sulfur, the spark of metabolism and scent of the sea. Together, they form the code that chemistry seems unable to resist. Wherever these 5 come together in the right proportions, under the right conditions, life appears to bloom. It's as if the universe itself has a favorite recipe, and it never quite forgets it. When Webb analyzed the light from K218b's atmosphere, those same fingerprints appeared in its spectrum. Traces of methane and water, hints of carbon dioxide, whispers of dimethyl sulfide. They combine in ratios that feel almost familiar, echoing the balance we see here at home. It's not identical. How could it be? But it's recognizable, like hearing the same melody played on a different instrument. This isn't coincidence. These elements are forged in the hearts of stars, created in supernovae, scattered across the galaxy in dust and gas. Every atom of carbon and oxygen in our bodies was once part of a dying star's final breath. The same process that gave birth to us also seeded worlds like K218b. We share ancestry with the very material that might now be forming life elsewhere. It's a humbling symmetry. The same ingredients that stirred in Earth's primordial oceans may be swirling now beneath K218b's hydrogen seas. There, they could be assembling into membranes, replicating molecules, simple forms of metabolism, tiny sparks of awareness in the cosmic dark. The chemistry doesn't care what planet it's on. When the conditions are right, when energy meets time and matter, the recipe fulfills itself. And perhaps that's the deeper truth Webb is uncovering. Not just that we are made of stardust, but that the universe knows how to make life again and again. The laws of physics don't play favorites. The same equations that govern hydrogen clouds and stellar birth also allow molecules to form, to link, to dream. If life is the universe's way of knowing itself, then this recipe is its memory, a pattern it can't help but repeat. From one world to another, across oceans of time and light, the same 5 elements are performing the same quiet miracle, turning chaos into order and matter into meaning. When we look at K218b, we're not just looking at another planet, we're looking at a reflection of the universe's favorite experiment. The one it's been running for billions of years. The one that, somehow, keeps producing wonder. Different world, same story, same ingredients, and perhaps the same spark that makes us all alive. From one discovery to the next, the same temperature appears again and again, 120 degrees Fahrenheit, the sweet spot where chemistry comes alive. Coincidence or cosmic design? In the cold expanse of the cosmos, where most worlds are frozen wastelands or blazing infernos, it seems almost impossible that so many potentially habitable planets share one unlikely trait: warmth. Not too cold to halt reactions, not too hot to destroy molecules, just the steady, simmering heat of about 120 degrees Fahrenheit, the threshold where chemistry begins to dance. Over and over again, across the spectra of distant exoplanets, Webb keeps finding atmospheres and surfaces bathed in that same delicate balance. It's the temperature of potential. On Earth, such warmth is found in the bubbling vents of the deep ocean, the hot springs of Iceland, the mud pools of primordial Earth, the exact places where life is thought to have first awakened. There, heat becomes a catalyst, speeding reactions without burning them away. Molecules collide more often, link more easily, experiment more freely. Life, at its core, is chemistry in motion, and 120 degrees is where that motion becomes music. On K218b, the balance is uncanny. Its hydrogen-rich atmosphere traps just enough heat to keep its oceans liquid and dynamic. The planet's steady orbit, locked in eternal equilibrium with its red dwarf star, ensures that temperature hardly changes. No wild swings, no frozen nights or blistering days. Just consistency, a global incubator, maintained for billions of years. If life began there, it would have had the rarest gift the universe can offer: stability. And yet, this number, 120 degrees Fahrenheit, seems to recur across other potential worlds too. TRAPPIST-1e, LHS 1140, b, and even some of the moons around gas giants in our own system, like Europa or Enceladus, hover around similar temperatures in their subsurface oceans. It's as though nature has chosen this point, over and over again, as the most fertile temperature for creation. Or maybe a fundamental truth, woven into the chemistry of existence itself. In biochemistry, there's a narrow window where complexity thrives, too cold and reactions slow to near stillness. Too hot and fragile bonds shatter. Between them lies a zone of gentle chaos, where motion and structure coexist, where molecules have time to meet and evolve before they break apart. It's a balance between order and entropy, creation and destruction. And again, the numbers lead us here. 120 degrees Fahrenheit. Is it possible that this is the universe's preferred rhythm? That across billions of light years, Whenever conditions align for life to emerge, the same gentle warmth is chosen as the cradle? If so, it means that life, wherever it forms, is guided not by chance, but by physics, by temperature, by energy. Perhaps this constant isn't just coincidence. Perhaps it's the echo of an underlying law, a cosmic tuning of creation. The same way gravity shapes stars and orbits, heat may shape life, drawing it again and again toward the same narrow comfort zone, the same thermal harmony. And if that's true, it means that every ocean shimmering at 120 degrees, whether on Earth or K218b, is connected by more than curiosity. It's connected by principle, by the universal mathematics of life itself, a number, a temperature. And maybe, just maybe, every living thing in the cosmos is born from that same constant, a shared warmth, written into the code of creation. Webb's instruments detect notes in light, tiny dips and peaks that together form a melody of molecules. Each note tells us a story of how a planet breathes. It may seem strange to think of chemistry as music, yet that's exactly what it is. When the James Webb Space Telescope studies a distant world, it doesn't see images or colors. It listens. It listens to the rhythm of light as it stretches and bends through alien atmospheres. Every molecule vibrates in its own frequency, absorbing light at precise wavelengths, creating a pattern of highs and lows, a cosmic score written across the electromagnetic spectrum. To the untrained eye, it's just data, jagged lines on a graph. But to scientists, it's a symphony. Methane hums in low tones, water vapor dances in the mid-range, carbon dioxide strikes a sharper note, and dimethyl sulfide, a whisper of life, plays a tune so faint it can only be heard through patience and silence. Together, these notes reveal the unseen, the composition, temperature, and behavior of entire worlds. On K218b, this melody is hauntingly familiar. When Webb transformed its infrared readings into spectra, it was like hearing a song we almost recognized, a pattern that echoed Earth's atmospheric harmony. Water, methane, carbon dioxide, all in concert. Then came the unexpected chord, the subtle signature of dimethyl sulfide, an alien note that changed the entire composition. Suddenly, the music became alive. Webb's instruments are, in essence, the universe's most sensitive microphones. They can detect fluctuations in brightness smaller than 1 part in 100,000. That means that even the faintest absorption of light by a single molecule can be heard, measured, and translated into data. It's like listening for a violin in a hurricane and still hearing it play. To capture this cosmic orchestra, Webb operates in perfect stillness. Its golden mirrors, floating 1,000,000 miles from Earth, must remain colder than any place on our planet. No vibration, no interference, no stray warmth to distort the notes. In that silence, the telescope becomes a listener of extraordinary grace, turning the invisible into sound and meaning. When scientists read those patterns, they can reconstruct an entire alien world's behavior. How fast its winds blow, how thick its clouds are, whether its air is calm or stormy, rich or thin, alive or inert, each molecule plays its part in this planetary symphony, resonating in harmony with its neighbors or in dissonance, hinting at imbalance. And if you listen closely enough, you can almost hear the breath of the world itself, the way its atmosphere cycles energy, the way heat moves from one hemisphere to another, the way chemistry interacts like chords rising and falling in endless rhythm. Every world has its song. Venus sings in sulfur and acid, Mars hums in carbon dioxide. Earth's melody is rich with oxygen and water vapor, a harmony only life could compose. And K218b, its music is deeper, slower, softer, played in the key of hydrogen and warmth. Its rhythm steady, its tone alive with mystery. Perhaps the universe has always been a symphony, and we're only now learning to hear it. Every spectrum Webb captures is a bar in that eternal composition. Every dip in light, a note played by some distant molecule. And as Webb listens, The melody grows, layer upon layer, planet upon planet, until the cosmos itself becomes a song about connection, chemistry, and creation. A song that says, "Every world has a voice. If only we are quiet enough to listen." Sometimes the absence of noise is the answer. No interference, no contamination, just the clean, clear voice of another living world. In science, silence is often where truth hides. The James Webb Space Telescope listens to the cosmos with unparalleled sensitivity, its detectors tuned to the faintest whispers of starlight. But for scientists, what matters just as much as what Webb hears is what it doesn't. The missing signals, the quiet gaps, the stillness between the notes. Because in that silence lies certainty. When Webb studied K218b, it found a remarkably clean spectrum. No signs of instrumental noise, no distortions from stray radiation, no miscalibrations, just a smooth, undisturbed curve, the unmistakable language of light passing through a real atmosphere. The data was so pure, so free of background clutter, that scientists knew instantly they were seeing something extraordinary. It's counterintuitive, but in astrophysics, silence is often proof. If a signal were contaminated, blurred by interstellar dust, distorted by solar particles, or misinterpreted by the telescope's sensors, it would show up as static, noise, or irregularities. But K218b's readings were pristine. The planet's molecular fingerprint stood alone, framed in stillness. No false positives, no interference from Earth's own gases or instruments, just clarity. It's that purity that gives scientists confidence in what they found. Dimethyl sulfide, one molecule, standing quietly in the void, repeating its presence again and again through every observation cycle. No background hum, no conflicting signal. Just consistency. The kind that only reality can sustain. And that's what makes this discovery so beautiful. It's not loud. It's not dramatic. It's not a cosmic shout. It's a whisper in the dark, perfectly formed and unbroken. A signal that endured a journey of over 100 light-years, unscathed, untouched. To find life, humanity had to build a machine so sensitive it could hear the silence between stars. A telescope that could detect a single molecule's breath across impossible distance. But once it did, the universe answered not with noise, but with quiet truth. In a way, it's poetic justice. For centuries, we've filled the sky with our own noise. Radio waves, transmissions, signals, all shouting into the void, hoping for an answer. But maybe the universe never needed to shout back. Maybe the proof was always there, waiting in the quiet. The silence isn't empty, it's honest. It tells us that what Webb detected isn't an illusion or coincidence. It's a real, physical, biological signature. It's the sound of another world breathing softly beneath a red sun. And that is the essence of discovery, not in the explosion of revelation, but in the moment of calm after, when everything else fades and only truth remains. Because sometimes the universe doesn't reveal itself in noise, but in its absence, in the perfect, crystalline stillness between signals, in the proof that requires no correction, no explanation, just silence. And in that silence, life. Webb's success marks the beginning of humanity's most ambitious survey, a search for life not just on one planet, but across hundreds of nearby stars. For generations, we've looked up at the night sky and wondered which of those points of light might harbor life. Now, for the first time in history, we can find out. The James Webb Space Telescope has proven that we can not only detect planets orbiting distant suns, but also read their atmospheric chemistry in exquisite detail, decoding the invisible breath of entire worlds. K218b was just the beginning. With its golden mirrors tuned to perfection, Webb can now analyze the light of hundreds of exoplanets within a few hundred light-years of Earth. Many of them are Hycean worlds, planets wrapped in hydrogen, with potential oceans beneath their clouds. Others are rocky, Earth-sized spheres circling dim stars, or super-Earths with thick, temperate atmospheres. Each one is a new experiment in nature's endless imagination. Teams of scientists around the globe are already lining up their targets. LHS 1140b, TRAPPIST-1e, Gliese 1061c. Dozens of names, once little more than catalogue numbers, are now becoming familiar, each a new possibility, each a candidate for that same whisper. Over the coming decade, Webb and its successors will study them one by one, collecting their light, mapping their gases, comparing their fingerprints, and with every new observation, the odds that we will find another signal of life grow exponentially. This is the beginning of what some call the biological census of the galaxy. Not a search for a single miracle, but for a pattern, for proof that life is not a fluke, but a phenomenon woven into the physics of creation itself. The ultimate question is no longer, is there life out there? But how common is it? Each discovery reshapes our understanding of what it means to be alive. K218b showed us that life might breathe hydrogen instead of oxygen, thrive under a red sun instead of a yellow one, and flourish in oceans we cannot see. The next discovery might show us life built on silicon, or chemistry that exists only at searing temperatures or crushing pressures. We're no longer searching for another Earth, we're searching for every possible version of alive. And Webb is not alone. Future missions, LUVOIR, HabEx, the Origins Space Telescope, will follow in its path, each one sharper, faster, more precise. Together, they will form a network of cosmic listeners, mapping our neighborhood in unprecedented detail. Within a few decades, we may have catalogued hundreds of atmospheres, measured their climates, and even watched their clouds drift and change. The age of wondering is ending. The age of knowing has begun. Humanity stands now at the threshold of a revolution, not of technology, but of perspective. For the first time, we are truly capable of answering the oldest question we've ever asked. Are we alone? And as Webb drifts through the quiet dark, turning its gaze from one faint star to the next, it's already whispering the answer. Not yet in words, not yet in sound, but in the soft rhythm of data, in the steady pulse of discovery. A new era has begun, an era where the universe itself becomes our laboratory, and where every point of light might be a home waiting to be heard. If life thrives on K218b, it's likely everywhere. The cosmos may not be empty. It may be bursting with unseen worlds, each quietly alive. For centuries, we've looked into the night and mistaken silence for solitude. The stars seemed still, distant, unreachable, points of cold fire scattered across an indifferent sky. But now, with the light of K218b decoded and understood, that illusion is beginning to fade. If even one planet beyond Earth carries the signature of life, the probability that others do multiplies beyond comprehension. It changes everything, not just scientifically, but existentially, because the moment life is confirmed elsewhere, it stops being rare. It becomes inevitable. Mathematically, the odds are staggering. The Milky Way alone holds more than 100 billion stars. Even if only a small fraction of them have planets, and only a fraction of those lie in habitable zones, that still leaves billions of possible homes for life. If K218b is alive, then life is not a miracle, it's a pattern, a cosmic instinct written into the fabric of matter itself. Perhaps every corner of the galaxy hides its own variations of that same spark. Some worlds may be shrouded in hydrogen, others in nitrogen or methane. Some may glow under twin suns, others orbit quietly around cold red embers. Each would evolve differently. Unique biochemistries, alien ecologies, unimaginable forms of intelligence, yet all would share the same underlying truth. They exist. And if that's true, then we are not early in the story of life. The galaxy may already be rich with civilizations, some ancient, some newborn, most perhaps unaware of each other, all separated by oceans of time and distance. The quiet night sky, once thought to be empty, may in fact be singing with the faint, overlapping harmonies of life. It's humbling to think that we might never meet them, never hear their voices, never see their oceans, but we will know they're there. And that knowledge alone reshapes our understanding of what it means to exist. K218b, then, is not just a planet, it's a revelation. A mirror showing us that we are not a cosmic accident, but a continuation. That the same chemistry that built our seas and skies is at work across the galaxy, repeating the same experiment with infinite variations. The universe is not a void waiting to be filled with life. It is life, vast, unfolding, and alive in ways we have yet to imagine. Every world that orbits its star, every cloud that holds its heat, every molecule that dances in the dark may be part of a grand, living continuum. The stars, once silent, begin to whisper back, and as Webb listens, the message becomes clearer. We were never alone. We were only early to notice. The universe is awakening, not because life is beginning, but because we are finally learning how to see it. As we gaze outward into the dark, we are really looking inward, seeing our own origins written across the stars. Perhaps life was never a miracle at all, but the universe recognizing itself. Every discovery Webb makes, every distant planet, every spectral fingerprint, every whisper of chemistry, reminds us that we are not apart from the cosmos. We are the cosmos. The atoms that make up our bodies, our oceans, our air, were once part of ancient stars that burned and died long before Earth existed. Those same atoms now form the clouds of distant worlds, the air of K218b, the molecules that may be breathing there beneath a red sun. When we look at that faint glimmer of light across 120 light-years, we are witnessing our own reflection, scattered through time and space. The hydrogen in K218b's sky is the same hydrogen that burns in our sun. The carbon in its potential life forms is the same carbon that builds our DNA. We are, in the most literal sense, related not just to that planet, but to everything that ever was. It's a strange, quiet realization that the universe is not a stage upon which life appeared by chance, but a living system that grows aware of itself through the beings it creates. When life blooms on a planet, any planet, it's not an accident. It's the cosmos thinking, feeling, and seeing through new eyes. K218b may be one of those eyes. Another place where consciousness, in whatever form it takes, looks up at its own sky and wonders, as we do now, who else is out there. Maybe their oceans glow softly under their red sun. Maybe they have no eyes to see, no voices to speak, but they exist. And in that existence, they complete the universe's reflection. Every telescope we build, every signal we catch, every molecule we identify, brings us closer to understanding that profound truth, that the universe doesn't need miracles to make life. It is the miracle. The laws of physics themselves seem to conspire toward creation, transforming chaos into pattern, matter into meaning, silence into song. When Webb peers into the dark, it isn't just mapping space, it's mapping us, our origins, our possibilities, the countless ways the universe expresses its own awareness. We are the cosmos trying to understand itself, and every discovery like K218b is another step in that awakening. So as we drift through the quiet dark, surrounded by stars and mystery, we are not searching for something foreign. We are searching for home, for the recognition that everywhere life exists, it carries the same spark that lives within us. Perhaps life was never the exception. Perhaps it is the universe's natural state, a reflection written in light, waiting patiently for someone to look back and finally see. The light that carried K218b's secrets traveled across a century to reach us, and in that long journey, it taught us something simple and enormous. We are part of a vast, living story. Tonight we saw oceans, a warm, global hush, molecules that read like a heartbeat, and a planet that holds time like a promise. Remember the quiet facts we traced: the dimethyl sulfide that hints at breathing seas, the steady red dwarf, the 120 degrees Fahrenheit balance that cradles chemistry, and feel grateful that you are awake in a cosmos that keeps revealing itself. Let that wonder settle at the edges of your thoughts like starlight on water. Breathe slowly. Imagine those distant waves, slow and patient, lapping beneath alien skies. You are safe. You are small and magnificently connected. Sleep now, carried gently on the tide of the universe,